Hello, and welcome to Backer Breaks It Down. Today, we are going to identify and analyze linear functions. Okay, so linear functions have a constant rate of change. Now, you can calculate rate of change using the formula y2 minus y1 over x2 minus x1, or you can also look to see how are the x values changing and how are the y values changing, and well, is it constant? So as you can see in the table on the left, as x is increasing, right, our x values are increasing by 3 each time, and the y values are decreasing by 6 each time. So that is a constant rate of change, okay? And we can calculate it by going -6 divided by 3 is -2, but no matter what, there's a constant rate of change, which means that table represents a linear function. Whereas the table on the right, we can see that the x values are increasing by 2, but the y values are increasing by 7, and then they're increasing by 11, and then they're increasing by 15. So there's not a constant rate of change there, okay? But linear functions have a constant rate of change. So I can look for this like constant pattern with the x's and the y's, or I can calculate two average rates of change, and if they're the same, then my function is linear. So let's take a look at an example. It says your aerobics instructor informs you that to receive full physical benefit from exercising, your heart rate must be maintained at a certain level for at least 12 minutes. The proper exercise heart rate for a healthy person, called the target heart rate, is determined by the person's age, and the relationship between these two quantities is illustrated by the data in the following table. Does the data in the table indicate that the target heart rate is a linear function of age? Explain your reasoning. Well, let's take a look at how each of our quantities are changing, okay? So I can see that in that first interval, the age is increasing by 10. It continues to do so throughout the table, okay? So my input values are constantly increasing by 10. So let's take a look at my output values. What are they doing? They're going from 140 to 133. So that's a decrease of 7. Then they go from 133 to 126, which is another decrease of 7. And I see that it continues to do this. It continues to decrease by 7. So the bottom line is I'm observing that the average rate of change is actually a constant rate of change, okay? Because like the output values are decreasing by 7, while the input values are increasing by 10. So our constant rate of change is -7/10. And when a function has a constant rate of change, it's a linear function. So let's talk about a general formula for the family of linear functions. Formulas of linear functions follow a pattern. Observe. Let me get out my highlighter, all right? So we've got the output quantity is equal to the initial value plus the rate of change times the input quantity, or as we very well know as y equals mx plus b. It's called slope-intercept form, okay? Now the constants m and b are parameters, and we are frequently asked to interpret the meaning of the parameters in a contextual situation. So the coefficient x, which I think we commonly call it the slope, in like a word problem, we wouldn't want to call it slope. We would want to refer it to as the rate of change. The initial value could be the starting value of the situation, or it could just be a value that remains like the same throughout, okay? But let's actually first create a linear function using the general formula, and then in the next problem we'll analyze one. So in example number 2 here, it says you have decided to buy a new Honda Civic, but you're concerned about the value of the car depreciating over time. You search the internet and obtain the following information. The suggested retail price is $20,905, and the depreciation per year is $1,750. We're assuming that to be constant, so we can write a linear function. Write a formula that expresses the Civic's value, V, in terms of the number of years of ownership, N. Right? So let's start with our output. Our output is V for the value. Now, the initial value of the Honda Civic was that suggested retail price. That would be the price that the manufacturers want me to pay to buy it. So $20,905. Now we're ready for the rate of change. Now, the value of the car is depreciating, which means it is decreasing each year. And it's decreasing by $1,750 for each of those N years of ownership. So this would be our function. V equals 20,905 minus 1,750 N. So what if they gave us this function or gave us a function and they asked us to interpret the meaning of the parameters, okay? So in problem number 3, it says that the relationship between the market value of your home and the length of time, x, you've owned your home since 2005 is modeled by the linear function v of x is equal to 1,250, I said that wrong, $125,000 plus 2,500x, where v of x is measured in dollars and x is measured in years. What is the slope of this line? And what is the practical meaning of the slope? Okay, well, here's our function. And the slope is the rate of change. And the rate of change is what's attached to that input variable of x. Therefore, the slope of this line would be 2,500. So what is it representing? Well, in a previous lesson, we talked about how you can interpret a rate of change. And basically, we want to say that the output quantity is either increasing or decreasing, and then by how much, how often. Okay, so observe, because I really didn't feel like writing it out. So I said the slope is 2,500, right? And I said that the market value of your home is increasing by $2,500 every year. So since the slope is positive, the value is increasing. Now that $125,000, right? That was the vertical intercept of the function. And its meaning here is it's the initial value of your home. Or even better, in 2005, the market value of your home was $125,000. So that's how we can identify and analyze a linear function with the general formula y equals mx plus b. M is representing that slope, or even better, that constant rate of change. B is representing, yes, the y-intercept, but I like to think of it as the initial value, or a value that is constant in the situation. And that's how Becker breaks it down.